मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Let us now look at some heat transfer applications of finite element analysis. As I told you in the last class, thermal problems or heat transfer problems have a lot of applications for manufacturing. I am going to concentrate only on manufacturing, not actually the thermal problems which are, say, dealt with in other areas of thermal engineering, for example, say heat exchangers and so on, though the concept which I am going to teach you is exactly the same as what you are going to apply or what you can apply for all these problems. There is no doubt about it, there is no questions about it. But nevertheless, after I teach this and when we go to case studies, I am going to give only problems from manufacturing, right. As I told you in the last class itself, the thermal problems application to manufacturing is very important and is the major step in welding problems, okay, welding, casting and so on, welding, casting and so on. Now, the thermal problems can be broadly classified into what we call as steady state and transient problems, okay. I hope all of you know what is a steady state problem and what is a transient problem. So, steady state problem is one where the temperatures do not change with time, okay. Transient problems are ones where the temperature is a function of time. Is that clear? Okay. Now, I hope all of you have studied this to a certain extent in your heat transfer courses. Probably some of you would have looked at the governing partial differential equations quite closely. Maybe a few of you may know the type of governing partial differential equations for a steady state problem and a transient problem. What are the types of partial differential equations? Can someone tell what are the types of partial differential equations? No, types of partial differential. Say for example, it can be classified into elliptic, parabolic and hyperbolic, okay. This is the type of partial differential equations into which you can classify any PDE, and that the steady state problems are governed by what type of equations? Do you remember? Elliptic, very good. So, now you know that steady state heat transfer equations are governed by elliptic partial differential equations, and transient heat transfer equations are controlled by what are called as parabolic type of partial differential equations. Okay, this is just to review what you know, and that this is what we are going to study. Now, in the first lecture, in today's lecture, I hope you will be able to complete it, or else it may spill over tomorrow or next lecture. Now, in this lecture we are going to look at the formulations for steady state and transient phenomena, and this we will follow it up with an example. Is that clear? We will follow it up with an example. Now, before we go to the finite element part, I have summarized here, okay, the equations, the governing equations which are important for the analysis of heat transfer. Look at the first equation. Are you all familiar with this equation? Okay. This is the heat transfer equation which all of you would have seen, right? Any doubts? Okay. So, what is K? Thermal conductivity, density and specific heat, okay. This is what we call as the governing differential equation, and this is very similar to what can you pick up a similarity between this and what we have done to our equilibrium equations that we have studied for stress analysis and so on, right. Okay, this is a general equation, or sorry, rather this is a specific equation, and this equation can be generalized a bit. What do I mean by generalization? What do I mean by generalization? Now K here, for example, has been assumed, okay, to be the same, or it has been or the material property K has been assumed to be isotropic, okay. It is the same in all directions, okay. You can in fact say that K may not be a constant, K may vary from one direction to the other, okay. K can be looked at like a tensor with Kx, Kxy, Kyx and Ky, and you can also look at K to have what are called as principal directions, okay, K1 and K2, right. And then in fact in any material we can have principal directions of K, K1 and K2, in which case this matrix which I have written here for K, where it is Kx, Kx, Kxy, Kyx, Ky, can be written as a, how do I write it if it is a principal directions? Diagonal matrix, correct. So K1 and K2, 0 and 0 here. Now this is, it is very important to understand this. Why? Because why do you think it is important to understand the principal directions and this kind of Kx, Kxy and so on? Why do you think it is important? I wanted to give an answer, but I thought that it is better that I know whether you understood this. Because principal directions of K1 and K2 is fixed with the material or the component, okay. X, Y, Z axes are axes chosen by you, okay. Say for example I am going to do a problem, okay, where some fiber is running like this, and that the K values in this direction and in this directions are say different, and say they are the principal directions, okay. Say one direction is 1 and the other direction is say 2, right. Suppose I say like this, and then these two are fixed, this 1 and 2 directions are fixed, but due to some reason it is not necessary, or due to some reason I may shift my x and y axis. In other words, it is not necessary that I should have my x and y axes to coincide with 1 and 2, due to some reason, you know, it may be, I just put a simple figure where x and y can be chosen like this, but the picture may be more complicated than this. Then I may choose x and y to be say in this direction, a different direction. Then it is important that the thermal conductivities are now expressed in terms of the x and the y coordinate system which I have chosen. Is that clear? And hence we write like this. But if you are doing normal metal, you know, like in the sense that say steel, most of the times we are not worried about the anisotropy of these metals, okay. In which case how do I write this thermal conductivity matrix, this matrix, how do I write this? K, K, 0, 0, that is it, K into 1, 1, okay. This is just to make this equation to assume a much more generalized form, okay. So in a very generalized form this equation can be written in this fashion. By the way, what is Q? Heat generate, what is it? I mean, what is it? What is the unit? No, what is it? Is it rate of heat generation or I would like you to go and have a look. I am not going to give you the answer, okay, all sorts of answers I am getting. So, have a look at that. Rate of heat generation, okay, internal heat, yeah, rate of internal heat generation. Have a look at that before you come to the next class, because you should be clear. These are all very fundamental things. You should be clear as to what are the terms that go into the picture. Okay, fine. So, in a very general case, I can write the equation in this fashion. Since I have committed myself to the task that I will do manufacturing problems, there are other aspects as far as this equation is concerned which enters into the picture. What are the other equations or other aspects that enter into the picture? What do you think are the other aspects? Because I have committed myself to look at, say, welding problem. What do you think are the other issues? No, we are now looking only at thermal problem. Okay? Expansion is important. When does expansion becomes important? Because when we look at a thermal problem and then have this as an input for a mechanics problem to look at deformation, then my coefficient of thermal expansion becomes important. But there are other things as well. Just think about it a minute. Like we are looking at manufacturing problems. What is so very great about manufacturing? Say a welding problem or a casting problem. Let's just look at these two problems. What is so very different from other things? Yes, that's it. So very good. So the temperatures are very high. It can vary quite a bit, okay, and hence K, rho, Cp, all these things may depend upon temperature. Okay. So this will make the problem highly nonlinear. The K may not be a constant, will not be a constant. Why may? Will not be a constant. Rho, Cp, everything would change with the temperature. So it is important that you realize this fact that K, whatever thermal or properties that we are talking about, may not be a function or may not be a constant, but may be a function of temperature, and that has to be known. See, many of the failures of doing simulation of manufacturing process comes about because of two things. One is not understanding, first of all, that these values are not a constant. That would make a huge difference. It can vary 2 times, 3 times, and so on. Number 2 is to get proper property values. That's also important, right? That's also important, that you get a proper property values. Fine. So we have defined what we called as the governing differential equation. Define what is called as the governing differential equation. What does this governing differential equation, let's forget about this for a minute. Governing differential equation require, what is it that we should have along with it? Boundary conditions. Now what are the types of boundary conditions that you can have? What are the types of boundary conditions you can have? Let's look at this picture. Say, let us now restrict ourselves to a plane, okay, plane problem. We will extend the other things later. Let's just look at this as a plane problem just for illustrating the boundary conditions per se. Okay. Now what are the types of boundary conditions that can exist in a problem? Heat flux and temperature. Okay. So a part of the boundary, in a part of the boundary there can be heat flux that can be given. Okay. Let us call this as say QB. Okay. Let us say that this is equal to QB. So how do we write QB? Say that heat flux may be, say, in this direction. So how do you write QB? The heat flux term how do you write it? K into dou T by say dou N or dou nu. Okay. Keeping the heat flux to be positive when the heat flux gets into the material, we can write this as say K into T comma nu. Okay. Now, we'll just see that how to modify it for more practical manufacturing problems. And what shape does it take usually? Okay, one is that you can look at it like this, or you can specify heat flux directly. Let's just come to that in a minute. But T comma nu can be written as, okay, T comma x LB. What is LB? What I am trying to do is to just chain rolling. Dou T by dou nu is equal to dou T by dou x into dou x by dou nu plus dou T by dou y into dou y by dou nu. Let me call dou x by dou nu as a LB and dou y by dou nu as MB, and let me call this as mu, LB and MB. These are things which you already know. Now, is that the only thing? Let's first theoretically put down the boundary conditions and let us look at the boundary conditions more closely in a minute, right? Okay. Now, is that the only way? Is that only way to specify the boundary condition? Convection. Okay. Let me capture this in a much more theoretical perspective. The boundary conditions are classified into what are called as essential boundary conditions and non-essential boundary conditions. Essential and non-essential boundary conditions. Now, let me ask you a small question. Let's not worry about what is essential and what is non-essential. We will come to that in a minute. Just before we proceed there, let me keep you thinking a bit. Now, let me assume or let me tell you that I have a body and that I am specifying the QB, okay, by this formula throughout the surface, right? I am specifying it like this. Now, can I solve this problem by whatever means, by finite element, because we are looking at finite? Can I solve this problem directly? And can you pick an analogy between your answer and what you already know? Do you understand? See, you already said that the boundary conditions can be temperature or heat flux. Heat flux, say for example, I am giving it in terms of a gradient like this, okay, K into dou T by dou nu, okay, that is the heat flux term. Now, suppose I say that this body, I am taking a body and that I am giving the boundary condition to be only consisting of QB or this, okay. Is it possible for you to solve the problem? If yes, why? If no, why not? No, very good. So, it is not possible to solve the problem only by specifying this. Why? You are bringing in a different effect. Okay. Okay, let me explain this and come back to this question. Your no is right, but your explanations are not right. Okay, let me come back to this. Let me go back to this steady state and transient. I thought you know it, but anyway, I will just review this because of your answer. I thought it's important that, see, there are two things. The steady state heat transfer, as I told you before, is governed by elliptic partial differential equations. They are called as boundary value problems, BVP. Many people call this as BVP, boundary value problems. Okay, in other words, what this requires is the boundary values, the values of, say, temperature or flux or whatever it is, that is what we are discussing now, that has to be given, okay, at the boundary, and these problems are called as boundary value problems. Do they require an initial condition? No. So, they do not require an initial condition because we are looking at steady state. We have forgotten about transient. Transient has happened. We are in the steady state condition. Okay. Many problems are of importance in this region, steady state condition. Okay. And hence, these problems do not require initial conditions, they only require boundary values, and hence these problems are called as boundary value problem. Is that clear? Okay. On the other hand, look at the transient problems. On the other hand, look at the transient problems. The transient problems are called as initial boundary value problems. Initial and boundary values, both of them have to be given. Okay. So, I would say initial boundary value problems. Is that clear? Okay. So, these are the things that have to be given: initial value, initial condition, okay, at time t is equal to 0, okay, and for the steady state problem I have to give only the boundary condition. Here also I have to give the boundary condition, of course I have to give the boundary condition, but apart from the boundary condition I also have to give the initial condition. I will come back to this because I think you have to catch this practically. Maybe you have solved heat transfer problems, but more, see, my problem is that many students are very good in heat transfer, but many students look at heat transfer problems as a mathematics problem, okay, as an initial value problem, as an initial boundary value problem, as a mathematics problem. There is lot more physics in it, okay, especially when I come to manufacturing. There is lot more physical things that are happening, and it is very important that you bridge this gap between what you know from heat transfer to what is happening in a actual manufacturing scene. You know, what is the analogy? It's very, very simple though, okay, but people make this mistake. So, I would like to explain that, but I hope now you are clear that these are the two things. One is boundary value problem, initial boundary value problem, initial plus boundary value problem. Let us come back to this. Okay. Now, let us just have a look at this. I think the clue is here. Why do you think? Yes, what you say is right. I can't solve a problem straight away by looking at this alone. Absolutely right. And you know the answer because we have done this before. We have in another circumstances we have said that it may not be possible to solve it. Yeah? Anyone with a clue?
The equation is second order in x and y, sir. We need some more conditions to solve.
No.
Just specifying qb equal to kT will not be sufficient.
Yeah, will not be sufficient, but where are you make that's why I said I agree with that answer.
Because it's second order in x and y, you need some more boundary conditions.
Yeah, I am saying, see, okay, fine. Let me give you another example, just to this thing. Okay, I said that, or someone said beautifully that temperatures can be specified. Suppose I say take the same body, I specify only the temperatures. I specify only the temperatures around. Right? Now I am specifying only temperature, only one boundary condition I am specifying. Now do you think that it can be solved or not? Because what he said, the answer he gave was that since you have given only one boundary condition, I can't solve this problem. Okay. Now I am saying that as you people told that that the boundary conditions can be classified into temperatures and flux, right? Now I am saying fine, I don't want flux, I want only temperature. Now can you answer whether I can solve this problem or not? Now you can solve it? No? Yes? See, this is very important for an engineer to realize how you can solve this problem, right? I mean, they are very, very fundamental. If I give temperature, yes, yes, majority say yes, but then why you solve it when I give temperature? Then you beat his answer because now I have given only one boundary condition.
That depends upon the type of problem.
No, I am not worried about the type of problem. Okay, I am only worried how, whether I'm okay giving this boundary condition or the other boundary condition. That's all. See, let us afterwards look at how to convert the physical situation into a boundary condition. That we will see it later. But at this point of time, I just want to know why. The answer is actually very simple. Now let me say, okay, let me give you a clue, because I mean this is not given in textbooks. This comes out of understanding a feel, for this. Let's look at this. Okay, I'm looking at a very physical answer. Let us look at this.
The equation consists of two variables.
No, this consists of, okay, let me, no, wait. See, let me give you a clue. I think you are off tangent, but I am happy that you are all thinking. But let me give you a clue. Let us look at this. What is this? This is a slope. So, I am specifying a slope. Okay. But what is that I want ultimately in this body? I want the temperature distribution, a unique temperature distribution. Okay. When I specify only QB, what is it that I am giving? I am giving, in other words, I am specifying a slope, right? Now do you catch it? Not yet. Yes, that's it. So, it is similar to constant of integration. I can give a slope here 40, 50, 60, 70, some value, say 70, okay, whatever be the units. Okay. I can make the body, I won't get a unique temperature because I have something like constant is exactly like that, constant of integration. Okay. The body can be at temperature ranges, say for example from 200 to 300, okay, still have the same slope, okay, and still have the same QB. The body can be from 500 to 700 or 650, still have the same slope, and so on. So, in other words, I am not fixing the temperature. The uniqueness of temperature is not specified by, I do not get a unique solution by specifying QB alone. Is that clear? Is that clear? Okay. So, the temperature part becomes important. So, the temperature part takes in what is called as the essential boundary condition. The heat flux part gives you the non-essential boundary condition. People call this essential boundary condition as Dirichlet boundary condition, I think Dirichlet boundary condition, and the other one as Newman boundary condition. Of course, because you are uniquely specifying. So, the question is, can you solve it only if I give temperature? Of course, you can specify the temperature alone and you can solve it because you can, okay, you can get a unique value. I am looking at it only physically, I am not going into the parabolic partial differential equation and so on, that aspect, but I am looking at it more physically. So, you specify temperature, you can solve it. Okay, I am going to confuse you a bit more, because this is important for us to later put boundary conditions, right. Now, suppose I am doing a problem where, say, welding, I am very interested in welding, I have done some work in welding and it is a very interesting topic. Okay. Now, I take a sheet, say for example, I take a sheet, okay, I am going to show you this example later, right. And now this sheet I will weld it with another sheet. These two sheets are joined together and welded. I am welding it at this place. Okay. Now, it is very clear, I am looking at the problem, that I am going to give heat inputs in this region, that is fine, QB is given. Okay. Now, what happens in these regions? If you physically look at the problem, tell me what happens. There will be convection heat transfer. So, convection, that means heat flux is going to go out. Okay, there is going to be convection heat transfer. So, I am going to put down here the boundary condition of the form. How do I put it down? How do I put, say for example, instead of this, I am going to say that Q due to convection is equal to, let me write it here so that it is clear, Q due to convection is equal to H into T minus T infinity or T atmosphere or whatever you call it. Okay. Now, what is it I have done? Instead of QB, okay, in these areas, I have now replaced this by a convection condition. Now, can I solve this problem? Now, see, please note this carefully. You can see this sheet, you would have seen it 100 times. Just take two sheets and weld it, right. I have told you that there is an essential boundary condition called temperature because I want to fix it. I want to say that, look, this is going to be the unique value, so I need temperatures. I have told you this. And if I give you only the heat flux term, I have already told you that look, you are giving a slope as correctly told by one student that the integration, it becomes a headache, and or the concept of integration becomes a headache, and so unique value cannot be obtained. All those things are very correct. Now the question that I am asking you is, look at this sheet, okay, and physically you see it, where do you put now temperature boundary condition here, and how am I going to solve this problem at all? Do you understand? Okay, let us forget about the element type used and all those things. As you correctly said that there is going to be heat transfer from this region. Okay. Now if that is the case, how am I going to put temperatures here? If I am not going to put, 1 minute, let me complete. If I am not going to put temperature here, how am I going to give the boundary condition to solve this problem, or can I solve this problem at all, is the question. Is it clear? Yes. So let us just look at it and tell me. Surrounding temperature is what I have. Can I put on the surface the surrounding temperature? I can't put, obviously. If you go and touch the surrounding temperature, say 35 degrees, in Chennai it may be 40 degrees or whatever it is, okay, always hot. So you can't say 40 degree, I am used to it, I will go and touch this place, right? Okay, it may not be possible. 1 minute, just a second, okay, let me finish it. So you can't put as boundary condition on the surface the atmospheric temperature, obviously that is totally wrong, okay, then I will get the same temperature throughout the bar. So because there is heat transfer that is taking place from the body to the atmosphere, right? Yeah, what is your answer?
No heat transfer along the pool.
No, that is correct, no heat transfer. We will come to that afterwards. There is symmetry, and I am going to take half the problem. What you say is absolutely right. We will come to that later. I will explain that in a minute. Okay, but here surface, I mean surface is exposed to atmosphere. So my question is this. Do you understand the question? My question is, I am contradicting myself. I said essential boundary condition is temperature. Okay, then only I will be able to solve the problem uniquely. You all agreed with me. Okay. And I said that non-essential boundary condition called Newman boundary condition is where I give QB, okay, and I said you can't solve a problem giving this alone, you all agreed. Okay, now I have posed you a problem like this. Okay, now I am asking you, if you have agreed with me on these two counts, tell me how do I solve this problem. How do you find out? Because that is a good thing. Okay, now you are saying that use this equation to find out surface temperature. How do I find out surface temperature? By using this equation. See, the equation can go only from right to left. It is not very easy to make it go from left to right. Knowing QC you can get T, okay, but how do you know? But because QC is what I can get knowing T. If at all I know outside, see, if at all I know T, my problem is solved. What am I trying to do? I am trying to find out the temperature distribution in this body, right? So it is not, I can't go from left to right. I can go only from right to left, so that is not valid. Yeah, no, what, see, look at what I want. I want to know, number one, can I solve this problem giving this? If so, how do I beat my earlier problem of specifying only non-essential boundary conditions? I am asking you, that is the question. What is the boundary condition I should give? Can I solve it? That is exactly what I am trying to ask you. Okay, see, how do I give? Do you understand everything? Everything is put. Is there anyone who is confused about this? Okay, is this a steady state problem? That is a good thing. Is this a steady state problem? Is this a steady state problem? Why do you say it is a steady state problem? Someone said yes. It is obviously not a steady state problem, because how am I going to weld this? I am going to change, or I am going to charge this fellow, the arc, to move along this direction. Okay, obviously when I am sitting here, okay, and say monitoring the temperature, initially I am happy, I am not hot, okay, and as this weld pool moves near me, towards me, what is going to happen? My temperature is going to increase. So it is a question of the temperature being a function of time. So obviously this is not a steady state problem, it is a transient problem. Yeah, initial condition is required, I agree. Initial condition is, let us not skirt the issue. We are still, you have not still answered my previous question.
So here both are same, no, sir, essential and non-essential boundary conditions. Because like QC varies directly with T, there's no differentiation involved. So there's no difference between.
Yes, that's correct. So let me rephrase your answer. That is very good. So in other words, what it means is that there is a big difference between giving this and giving QB. The big difference here is that I am fixing the slope with respect to T atmosphere. So the uniqueness is obviously satisfied automatically, okay, because I am fixing the slope, or in other words, it is something like giving that constant, that integration constant. I am fixing the slope. When I say the slope is 300, one side is obviously 40 degrees, period. Okay. So I am fixing the slope, right. So you have to be careful in saying that if I give heat flux QB, I can't solve it, but at the same time I can remove singularity, that is the word, okay, when I specify heat transfer coefficient or convection boundary condition. What is this like? This is similar to your force and displacement boundary conditions which you had given in your earlier classes, okay, where if I told you that if I give force, I will not be able to solve the problem, force alone, I have to have displacement or else I will not have uniqueness of result. On the other hand, if I specify this kind of QC, okay, for this problem, then I will be able to solve the problem without much issue. Is that clear? Any questions? Now is it clear, or no, not clear? Okay. Now let me recapitulate. See, this is important for doing all practical problems. Let us recapitulate. I said, you tell me whether you have understood this point. I'll just tell one point after the other. I said giving QB alone, it can't be solved. Understood. One. I said that this is basically because there is a slope that is maintained, or dou T by dou nu is given, okay, or dou T by dou n, however you call it, that is what is given. Then that is not unique, because when I integrate this, T plus a constant will come, okay. So when I specify just the slope, say 300 or 400, slope is 400, it can be between, okay, say 500 and 100, or it can be between 600 and 200 and so on. So it is not unique. So by specifying slope alone, I can't solve the problem. Agreed? Okay, that is what I said. So I said if you give temperature, this problem does not exist. Agreed? Fine. But I said that in practical problems, as a boundary condition, I may have to give this convection as a boundary condition. Okay. Convection is something like heat coming out, obviously you know it. But I asked the question whether I can solve this problem. Okay. Then I said that yes, you can solve it, or one of you answered it very well, that it is possible to solve it. Basically because now it is not that I am specifying slope, but I am specifying a slope with respect to TA. Say when I said 400 and 500 and 100, 400 is the slope and 500, it can be 500, 100, 600, 200 and so on. Here what I am trying to say is I am not only specifying 500, but I am also specifying the lower limit 100. So obviously that higher limit is fixed, that is T. Okay. In other words, this fellow here pegs down the result physically. I want you to understand physically, there are other things to it. Physically you can say that this fellow here pegs down the result. Is it clear now? So these are the boundary conditions that you give. So it is very important you recognize what is the boundary condition you give. And one of our friends here said that what about initial condition? Obviously for this problem you have to specify what is the initial condition as well. So what can you take as an initial condition? Ambient temperature, okay, unless you do some preheating or you do something else, okay, we can assume that the sheet has what we call as the ambient temperature. Now, let us just go ahead a bit to understand this problem. How am I going to give this heat flux, the torch that is going to move, okay, due to arc welding? So, for example, how am I going to give this heat flux? This is the Q input. Okay, this can be directly given. I need not have to go to K and so on. Okay, this is the heat input due to arc can directly be given as QB. Okay, and there are distributions to it. So, for example, you can say that the heat or the energy that you give in order to weld it can be distributed, say, in a normal sense with respect to distance. Okay, we will talk about this again later in the course, or maybe after we go through some theory. Okay, right now it is important to understand that it's possible to give this. Okay, we can give this as an input. The next issue that someone said is symmetry. Okay, now in other words, what he means to say is, why do you want to solve this problem taking both the sheets, right? Okay, and that if you take only one sheet, that's a very good answer. If I take only one sheet, that suffices it to analyze the problem. Okay, but the only condition I have to put here in order to solve this problem is that this side, from this side, there is no heat transfer, or this side can be considered as insulated, because the other side, it is like symmetry boundary condition. So, other side will have the same temperature distribution. So, the slope there at that point will be 0, and so there will not be any heat transfer coefficients. Yes, heat input is given, okay, in these nodes perpendicular to it. Okay, we will talk about the elements later, but let me put it like this. Okay, let's say, let me put the third dimension. Right now, heat input is given, say, in this region at the top face, say XY phase, and symmetry boundary condition is applied in the other phase which is perpendicular to it, that phase. Is that clear now? That we are not giving. Clear? Okay, fine. So, that is the practical things that we have to achieve. Knowing this, actually our job is very simple. The next step is very simple. What is it that I have to do? For the governing differential equation, I have to write down a functional. Okay, I have to write down a functional. So, the functional, so let us not go into the details of how to derive this functional. It can be very well nicely derived. So, but let us just say that this is the, have a look at that. This is the functional that we are going to put. Okay, it consists of all the terms that you want, and Tf is the final, actually this is Tf is Ta, or so on. Okay, all the types of boundary conditions, in sense that both Qc and Qb are there. Now, Tj, T delta here, okay, is dou T by dou x and dou T by dou y. Okay, that is what I have written here, dou T by dou x and dou T by dou y. The del operator is dou by dou x and dou by dou y. So, we are only looking at 2D, so that dV can be converted to ds, and this to L. Right. So, once we know functional, our job is quite easy. It is not very difficult. All of you by now are familiar as to how to convert this into a finite element form. Okay. What is more important is to understand what is the governing differential equation, what is the boundary conditions, how you give in a practical problem boundary conditions and so on. Okay. But because once I come to that level and write down the governing functional, okay, the problem becomes quite straightforward. I want to convert this into a finite element form. So, what is the next step I am going to do? What is the next step I am going to do? Wait, you're jumping, let's go step by step. First thing is I have to write down T in terms of the nodal coordinates. Now, what is the field quantity or variable here? What is the variable in those cases you had U, V, W and so on. What is the variable in this case? Temperature. Okay. So, the interpolation function or the shape function should be able to interpolate the temperatures. So, if I say that say here T1, T2, T3, T4 are the unknown values or values to be obtained, where 1, 2, 3, 4 are the temperatures of these 4 nodes. So, we can write down T as N T, right, the same fashion as we did U, V and W. Is that clear? Okay. So, T N, let me call this as T, okay, T1, T2, T3, T4. Okay. Now, what else do we need in this? What else do we need? Look at this, look at the functional, look at the functional and look at this. So, what else do we need? Those are the things. What is my strategy? Let us first understand my strategy. I will do that in the next class, but let me understand the strategy. What I am going to do is I am going to expand or extend or write temperature in terms of nodal temperature, okay, gradients in terms of nodal temperature, okay, substitute it into my functional equation, then differentiate it with respect to T in order to minimize the functional, period. It is very straightforward, okay. Or in other words, extending, this can be written as just to no, what did we call? B, correct, that is it. So, this is similar to B, right, into T, very good. So, we will develop this in the next class, but that is exactly how things work, right. Substitute it and we will derive it. We will continue this now that physically you have understood, okay, these things. We will continue with the derivation in the next class.